Hello, so today I'm looking at M3 International A-Level January 2014. This is question 3. A light rod AB of length 2A has a particle P of mass M attached to B. The rod is rotating in a vertical plane about a fixed smooth horizontal axis through A. Given that the greatest tension in the rod is 9 mg/8, find to the nearest degree the angle between the rod and the downward vertical when the speed of P, the particle, is this. So to try to understand what this looks like, we have this rod and there'll be a mass attached to one end of it at B, and the rod is rotating in a vertical plane. So if we take this to be the vertical plane and this to be the horizontal plane, then the rod is rotating in a vertical plane about a smooth horizontal axis through A. So here is point A, and so my axis is going here into the page. Okay, and the page is the vertical plane. So I can now try to draw this. Now here they talked about two different places. They talked about when the tension in the rod is greatest, and then they talked about this other position where the rod has a downward, an angle with a downward vertical, and the speed is this thing. So first of all, looking at when the tension is the biggest, well, when you have a rod moving in a vertical plane, the tension will be the greatest at the bottom. And so if I just draw what this looks like, so I have the axis is here, kind of going into the page, and then B is here, and I know I will have the weight. They said the mass was M, so the weight is mg. The tension will be towards the center of the circle in this rod, and they told me that the tension was 9 mg/8. And as this is moving in a circle, then I know the acceleration towards the center of the circle is either v²/r or r omega squared. Now in this case I've been given some information to do with the speed, so I'm going to use this for my acceleration rather, and I don't have any information about omega, so I'll use v²/r here. So here let's call this v²/r, where r is the radius of the circle, and they told me that the length of AB was 2a, so therefore the radius is 2a. So now I can write down an equation using Newton's second law towards the center of the circle, and I will do forces towards the center of the circle minus forces away from the center of the circle equals the mass times the acceleration. And so here the acceleration is whatever the speed is at this moment, let's just call that v², over the radius 2a. Tidying this up, I can see that I have m everywhere. Oops. So I can cancel m, I divide through by m, and I would quite like to know what this velocity is at this point. So let's work out this velocity. So I will have 9g/8 minus, well, is actually like 8g/8. So I could, and I will end up with here v²/2a, and here 1g/8. And so I could multiply both sides by 2 and multiply both sides by a, and so I end up with v is ag, if I square root the top and bottom, over 2. So that gives me the velocity at this lowest point, and I'm interested in that because, well, it's the only thing that I can actually work out here. But then I can find the relationship between the velocity here and when the particle is at this other position, with where the angle between the rod and the downward vertical is an angle of theta, and the speed is this at this other point. So If I kind of draw what's happening, then I had this initial position, which was when the rod was vertical, and then the rod will move around in a circle, and so the particle will end up at some other angle here. Here the speed is v, which is what I just worked out there, and then here the speed is this other value that they gave me here, which is root ag over 20. So how do I link these two things? Well, I know that energy is conserved, so I can say the energy that is here is equal to the energy that the particle has here. So the energy that it has here is kinetic energy using this velocity. There's some kinetic energy here too, and I can say that the gravitational potential energy here is 0, and so here the gravitational potential energy will be mgh, where h is this height here. Now, I know that the length of the rod was 2a, so from here to here is 2a, and also from here to here is 2a. So if I just draw in this triangle here, I know that this, using the hypotenuse and this angle, is 2a cos theta, and so therefore I can write an expression for h as 2a from here to here minus 2a cos theta from here to here, and use that to write down what the gravitational potential energy is here. Okay, so we have the kinetic energy in the beginning, so half times m times v squared, and so this squared gives me ag over 4. We said there's no gravitational potential energy here, so that will equal the kinetic energy here, half m times this squared, plus the gravitational potential energy that it has here, which will be mg multiplied by this height, which we said was 2a minus 2a cos theta. So dividing everything by, dividing through by mg, this happens. I can also divide by a. I'll just tidy it up a bit because I'm losing sight of what actual numbers I've got here. So here I have a quarter times a half, a quarter times a half. Here I have a half times 1/20th, and here I have 2, and here I have minus 2 cos theta. So now to get an equation just, to rearrange this to give me the value of cos theta, I'll pop this over here and this on the left-hand side, on the right-hand side. So on the left-hand side, I will have 2 cos theta, and on the right-hand side, I will have 1/40th plus 2 minus 1/8. And popping all of that in my calculator, I get 19 over 10. So then to work out theta, I'll do inverse cos of, divide both sides by 2, so I end up with 19 over 20. Okay, so inverse cos of 19 over 20 gives me, to the nearest degree, that will be 18. And you're done. So I hope you found that solution helpful. Please click like if you liked it, and good luck with your studies.